Hey everybody, in this next video lesson we're going to talk about nuclear fission. Humans were first exposed to the concept of nuclear fission back in the 1940s with the dropping of the atomic bombs on Hiroshima and Nagasaki in World War II. And the science behind it is pretty simple, to be honest, but it is very powerful, as you will soon learn. Now, what happens in fission is that we take a stable radioisotope of uranium, uranium-235, and we shoot a neutron at it. That neutron gets absorbed by the uranium-235 and turns to uranium-236. The neutron gets absorbed, becomes super unstable, and then splits up into two daughter isotopes. Now, in the process of that splitting up, give off a lot of gamma rays, and lots of heat is released. Talk more about that in a second. But also, 3 new neutrons get released into the space surrounding the uranium. And if there's more uranium-235 around, well, this reaction will happen again and again and again. And so you can see how they came up with the concept of the chain reaction. 1 makes 3, makes 9, makes 27. And it's a runaway exponential growth of splitting atoms, all of which releases energy. Now, 235 is the fissionable uranium. There are multiple isotopes of uranium, all of which are radioactive, but this is fissionable uranium and also plutonium-239. These are the 2 most common fuel sources for nuclear fission. The amount of energy produced from nuclear fission is extraordinary. Compared to a chemical reaction that can produce a lot of heat energy, this is nothing compared to the amount of energy that can be released when a nuclear reaction occurs. In chemical reactions, we know that matter and mass must be conserved. All the matter that goes into a reaction must come out, and the energy released or gained is based on the energy of the bonds being broken or created, that potential energy either being converted to kinetic or kinetic being converted to potential. But in a nuclear reaction, mass is not conserved, which is why it is not a chemical reaction. In fact, when uranium absorbs the neutron and splits into its 2 daughter isotopes, there is less mass in the daughter isotopes than there was in the original uranium-235. We call that the mass deficit. So in other words, the mass gets converted to energy, and that energy is given off in heat. This conversion of matter to energy is made famous by Einstein's E equals mc squared. The c in this case is the speed of light, 3 times 10 to the 8th meters per second. So that's an incredibly large number, and that number is squared. Now, we don't need a ton of mass multiplied by the speed of light squared in order to produce a sizable amount of energy. 1 kilogram of uranium-235 is equivalent to 20,000 tons of dynamite in terms of the energy released. So in summary, what makes nuclear reactions different than chemical reactions is that matter is not conserved, and in this case, matter is converted to energy, and that energy can be released in the form of an explosion, or if it's controlled, can be used to run nuclear power plants, but more on that in a bit. I want to show you a little computer simulation to help illustrate this concepts of fission and chain reactions. Check it out. All right, here's a little computer simulation that I'm going to show you. We'll take a look at nuclear fission in a couple different stages. This first one is just going to show you basic nuclear fission. This little gun is going to be able to fire 1 neutron at a uranium-235. It's green uranium-235, which means it's fissionable material. And when I fire the neutron, it becomes 236, and then it splits. And as you can see, it releases 3 neutrons in the process. Let's do that again. It absorbs the neutron, gets super unstable, decays, and 3 neutrons get thrown out. Let's talk about nuclear chain reactions now. So I have set up a situation where I have a mixture of uranium-235 and uranium-238, and once again I got my little neutron shooter. Now, uranium-238 is not fissionable, and if you get it hit with a neutron, it's just going to turn to uranium-239, and that's going to be basically just nothing. Nothing's going to happen. But if one of those neutrons hits a uranium-235, well, then it's going to split off, and it may strike another uranium-235, as you saw, which may cause another uranium-235 to explode. But if those neutrons get hit by uranium-238 or they run into a uranium-239, well, then nothing happens, and there's not a chain reaction. But what I can do is reset this situation and reduce the amount of uranium-238 and have a higher concentration of uranium-235. This is what is known as enriched uranium. And if you have enough enriched uranium, then you can basically have a chain reaction that causes more uranium to explode because there's less uranium-238 to absorb those neutrons, those loose ones that get shot off. Well, that didn't really react much of my uranium-235, so let's reset and take even less. Let's aim my shooter up here and see if I can get all of these to explode. Loose neutrons just happen to not hit any of these in the bottom, and so let's reset my nuclei and let's add more nuclei to the mix. So if I can pack a higher concentration of nuclei and shoot a neutron, maybe I can get all these to react. So there you go. Each one of them strikes another nucleus, causing more chain reactions. Now let's fill this thing up with 100. And here it goes. And as you can see, all the fissionable material has been used up. But I can slow down the chain reaction if I mix in a little bit of another uranium isotope, uranium-238 or uranium-239, and it will stop the chain reaction from happening. Now, another way to stop the chain reaction is in a situation like a nuclear reactor. Now, the reactor core has basically little pockets of fissionable uranium-235. And as you can see, I'm moving these control rods. Now, what happens here is if I don't have the control rods and I fire the neutron, you're going to get chain reaction, kind of like we saw in the last slide. All the uranium will fire off, releasing its neutrons, and the chain reaction, as you can see, is moving from right to left. But I can slow this down if I add these control rods in, and it will basically stop or isolate the chain reaction to just one pocket of this nuclear reactor core. So I fire the neutrons again, and not much happens. I can fire them again, a little bit of action over there on the left, but everything stops. But if I can basically move these control rods, what these control rods do is actually block or soak up any loose neutrons to keep them from reacting with other uranium material. And the control rods are the same way that nuclear reactors control a nuclear reaction by moving them in or out. The further out, the more nuclear reaction occurs, and the further in, the less nuclear reactions occur. And so you can control how fast the reaction happens by adjusting the control rods in or out. Now, if you have the control rods all the way out, you may cause a runaway chain reaction, which might produce so much heat that it melts down the reactor core and blows the top off your containment vessel, and the containment vessel then spews radioactive material into the atmosphere. So the control rods are a really, really, really important component of a nuclear reactor core. They control how fast a nuclear reaction goes. I showed you this in the simulation, but let's take some notes on it. An uncontrolled fission reaction is one where the fission just runs without stopping, so there's nothing to stop the neutrons from hitting other uranium-235, and the reaction just produces more and more and more and more energy. The reaction happens almost instantaneously because the neutrons that get fired off from the splitting of the first nucleus are traveling or approaching the speed of light in terms of how fast they're running. And so they're hitting next uranium in line, and those uraniums are hitting the next uraniums in line. And so this reaction, chain reaction, happens almost instantaneously because things are traveling so fast. An atomic bomb is an example of an uncontrolled fission reaction, and the reaction will continue until all the fissionable material has been used up and all the energy gets released all at once, rather than slowly over time. On the other hand, a controlled nuclear reaction can be done so by using those control rods that I explained to you in the computer simulation, or also you can control a nuclear reaction by having less purified or less refined uranium. So if you've got, once again, like I showed you in the computer simulation, a mixture of uranium-235 and other isotopes of uranium, the chain reaction will not happen quite as quickly, and you can slow it down and control it. What you're looking at is a schematic of a nuclear reactor. And in a nuclear reactor, what happens is the heat that is generated from the nuclear reaction is released. And what we've got here is the nuclear reactor and the control rods in this pink loop. So this is the reactor loop. This is water circulating through the reactor, and it picks up the heat and transfers its heat to a second loop, which has water that is inside this blue container, and it's going to transfer its heat boil the water to steam. The steam then turns the turbine, and the electricity flows out to homes or businesses. And that blue loop is enclosed as well. So the pink loop and the blue loop don't actually come in contact with one another. The heat is exchanged through pipes. Now that blue loop is continuously circulating. In addition to that, it's getting cooled by a third loop of water, which are then connected to those cooling towers, those signature concrete towers that you see as a symbol of a nuclear power plant. Is just more water that's circulating through the middle loop to try and keep the water in here cool so it's not completely boiling. And if you spring a leak in the reactor core, that's a terrible situation. And so we've got a containment structure inside that, which is basically many meters thick of concrete and lead. And so if this reactor core doesn't work properly and begins to melt down, then hopefully all of that radiation is contained inside that structure. And if that containment structure is breached, as in cracked or the top blows off, then we're all in real big trouble. That's what happened in Chernobyl back in 1986. Now, once those reactor core fuel rods get used up, then they get extracted from the reactor, and then they get stored in 12 meters of water and cooled for decades. That cool rod is still reacting, and because of that, we need to keep it from getting too hot, and that's why it's stored in really big tanks of water. And the water is also a specific type of water, heavy water, which shields the radioactive material, and it picks up those neutrons that get fired out from that decaying uranium and keeps from the reaction getting too hot and continuing to run. But those get stored in cool water for 10 years or so. After those rods are cool enough to handle, they may be shifted off-site and buried several hundred feet deep and encased in concrete so that nobody ever comes across them, because these will continue to be radioactive for many hundreds, if not thousands of years, if you remember our conversation on half-lives. Spent fuel rods are called HLW, or high-level waste, whereas medical and other industrial waste is considered low-level waste, and low-level burial sites are basically just certified landfills that are designated for radioactive material. Well, that takes care of this video lesson on nuclear fission. Thanks for watching.